Hey guys, welcome back. So in this video we will be learning about counters. What is counter in digital logic? So a counter is nothing but it is a digital electronic device. It counts the number of times that an event occurs using a clock signal. Here with each clock pulse the count changes, such as in the up counter where the count increases by 1. Counters are built using the flip-flops and they follow the custom sequences, like they count the numbers from 0, 1, 3, 2, and they act as a frequency dividers by reducing the input clock frequency. So there are two types of counters, asynchronous counter and synchronous counter. So in the asynchronous counter there is no clock, there is no common clock for all the flip-flops. Flip-flops are there but there is no common clock. Only the first flip-flop is driven by the main clock, and other flip-flops they are triggered by the output of the previous one. So as you can see, this is the asynchronous counter that we have. So what is this asynchronous counter? It is basically that we have a flip-flop. Here we take the example of JK flip-flop. So J, K, Q and Q bar. So this is the normal JK flip-flop. Here it is guided by a clock signal CK, and there is an output Q0. But in the other flip-flops, this flip-flop, this flip-flop, this flip-flop, the output you see Q1 and the clock you see is nothing but the output of the previous flip-flop. So there is no separate clock, it is just the output of the previous counter. For this the clock is nothing but the output of the previous counter. For this the clock is nothing but the output of the previous counter, and so on. So we have this sequence of JK flip-flops and we have the outputs Q0, Q1, Q2, Q3, and there is a high signal for all this. For there is a common high signal. So this is the clock signal that we have, and this is the outputs Q0, Q1, Q2, Q3. So Q0 will be a continuous output guided by a clock, so it will be in this form, whereas Q1 will be having some delay, Q2 will be having a little larger delay, and Q3 will be having little larger delay compared to Q2, because these doesn't have separate clock signals, so there will be a delay. So this is the asynchronous counter circuit diagram and the pulse diagram, timing diagram. The synchronous counter, where on the other hand is that it uses single global clock, and that global clock will derive all the flip-flops simultaneously. So all the outputs will change in the parallel. So you can see there is a clock signal here. So this clock signal is used everywhere in all the flip-flops. This flip-flop, this flip-flop, this flip-flop. So same JK flip-flop is there, Q bar is there, same outputs are there, Q3, Q2, Q1 and Q0. But here we have that high, which is VCC, and VCC is guided to both these two inputs, J and K, J and K. So there is a clock input. So clock input is common. So it is not that there is only one clock input for only one flip-flop. Clock input is there for all the flip-flops. So the next thing that we have to note here is that Q0, which is the output of first flip-flop, and Q1, which is the output of second flip-flop, they both are driven to an AND gate, and the Q, output of the third flip-flop, is provided as an input to AND gate, and the J input is provided as the input at the AND gate. So what inputs we have at the AND gate is the outputs of the flip-flops, respective flip-flops, and the J signal for the flip-flops. So the first is anyhow guided by the VCC. For second, third, we are having this AND gate combination. So what is the timing diagram for this? So you can see the clock pulses are there, 1, 2, 3, 4, 18, like that. So here what we have Q0, Q1, Q2, Q3. Here same thing happens, that there is Q0 which is continuous and which is very active signal, whereas Q1 is a little delay, Q2 is slightly more delay than Q1, and Q3 is more delay compared to Q2 and Q1. So that's why we have the count signal and there is a delay in subsequent outputs. So that is the difference here in the synchronous counter. So what is the main difference we can see is, here in the timing diagram we were not we were only using the clock against the outputs, but what is happening over here is that we are representing the count as well. So count from 0, 1, 2, 3, 4 up to 15. So So here you can see that its main advantage is it can operate at higher frequencies, as it does not suffer from delay, because the same clock is there. The same clock is applied to every flip-flop. So it is also called as parallel counter. For synchronous, same clock is applied to every flip-flop. So for this we have the same clock. So you see, at the same clock we are having this same thing. So for this we are having the same. I think the clock pulse is similar to all of this, whereas I think here the clock pulse is different. So for this one it was different. So for this one there was no clock pulse, it was guided by the previous output. This was guided by the previous output, and this was guided by the previous output. But here we can see that we have the clock pulse which is there for all the counters. So from the circuit diagram, Q0 responds to every falling edge. Q0 responds to every falling edge of the clock, and Q1 depends on Q0 and Q2. Q1 depends on Q0 and Q2. So this Q1 and Q2, Q0 and Q2, this depends Q1. Q1 depends on Q0. Q1 depends on Q0. Q2 depends on both Q1 and Q0. So this Q2 depends on both Q1 and Q0. Q3 depends on Q2, Q1 and Q0. Q2, Q1 and Q0. So all flip-flops change simultaneously under the same clock. What it is telling is that there is a dependency, direct dependency of Q1 on Q0, Q2 on both Q1, Q0, Q3 on all these three. So there is dependency. That dependency is not seen here. So that is the difference between asynchronous and synchronous counter. I hope you understood the difference between asynchronous and synchronous counter. The next type of counter that we have is a decade counter. I think decade counter is nothing but we have the clock pulse from 0 to 10. Okay, then we have the count for Q0, Q1, Q2, Q3. So for decade counter, decade means 10, so it will count from 0 to 9. Okay, so for clock pulse 1, this Q0 will be activated. For 2, Q1 will be activated. For 3, Q1 and Q0 will be activated. For 4, Q2 will be activated. For 5, Q2 and Q0 will be activated. It's just like whatever the clock pulse is there from 0 to 10, so the respective binary equivalent of that, so that will be activated at the output end. So for 2 we have the binary equivalent 1 0, so Q1 is activated. For 3, both Q1 and Q0 are activated, because for 3 it's the binary 0 1 1. So Q1 and Q0 are activated. For 9 we can see Q3 and Q0 are activated. So it's like that. So this is a decade counter, wherein we again have the JK flip-flops in series, and we have a clock signal. And here also we don't have all clock signals. So one clock signal is there. The next clock signal is the output of the previous flip-flop, like that. And another thing is we have a clear signal here. I think this clear signal is used to reset the output. We will check that later. The same thing is there. VCC voltage is there, and it is applied to both the inputs J and K. So what is Q0 here? Q0 is just taken up. The changes is not happening at Q0. At Q1 also it is not happening. At Q2 also is not happening. The change is only happening at Q3, wherein Q3 is taken along with Q1. So Q3 and Q1 are taken. So an AND gate is connected from to both Q3 and Q1, and output is fed to the clear input, because the binary representation of 1 0 is 1 0 1 0. When both Q3 and Q1 both become 1, okay, I think for 1 0 1 0, I think for 1 0 1 0, for Q3 and Q1, when both they become 1, I think it is just to make a 0 signal over here, so that when we make a 0 signal, that 0 signal can be given to a clear. Okay, activating the clear input, so that counter resets at 10. Okay, I think the actual count here, as we know, clock pulse is from 0 to 9. Okay, 0 to 9. So the next thing, 10, is not an actual clock pulse. It is just acting as a reset, because we have to reset the clock, right? After the decade completes, we have to reset the clock. So this is just to reset that clock, and to reset we are using the clear signal. So that is the thing why we are using the clear, to reset that clock. And for this we need to make 0, right? We need to get a 0 signal. So this 0 is made through this Q1 and Q3, and that 0 is made and 0 is fed to this clear signal. So that is the decade counter. So I hope you got all the different types of counters in this video.